In this video, we'll talk about composition of functions and compositions of rates of change, talk about how we can try to differentiate composite functions. We've dealt with a lot of different types of functions and find their derivatives before. We have trig, we have exponential, we have polynomials, all of those are great, and we know how to combine functions to find more complicated derivatives over the product rule. The one type we have not yet dealt with are composition of functions, and that's because they don't work nicely in terms of how we combine derivative of smaller functions into the derivative of the composition of two functions. For example, we can think of the function x to the sixth, which we can differentiate. The derivative of that becomes 6x to the fifth. Great. But I can write x to the sixth as x squared cubed. That's how powers work with nested powers. So I need to find some way to get from the fact that this x squared differentiates to 2x, and the x cubed part differentiates to a 3x squared, and somehow combine these two together to end up back at 6x to the fifth. It's even less obvious here how to do this. So we're going to step back and look at these compositions in general and think of what might want to happen to these rates of change and how that might lead us to a rule for differentiating these guys. So things that we can't yet differentiate because we don't know how to handle composite functions. Things like sine of 2x. Fairly simple function, but I can't differentiate that directly because I don't know what to do with that 2 that's attached to the x inside. However, I can differentiate this function by a more roundabout way. I can use a trig identity to write this as 2 sine of x cosine of x, and then I can use the product rule to differentiate that, which will give me a 2 times a sine times the derivative of cosine, which is negative sine, plus a 2 derivative of sine is cosine times a cosine. So I get 2 cosine squared x minus sine squared of x. And if you recognize that trig identity, this is 2 cosine of 2x. You can see it still involves this cosine, which is the derivative of sine, but there's this 2 hanging around out front that seems kind of out of place. You can do the same thing with something like e to the 3x by writing this as e to the x times e to the x times e to the x and doing a product rule on that. And when you do all of that, you'll get to a derivative of 3 e to the 3x. Again, still has this e function, which we expect from it being e to the x, but there's this 3 hanging around out front that again feels out of place. What should the formula for a derivative of a composition look like? We'll talk about this via an example. So let's say you're trying to climb a mountain, and P as a function of h is the air pressure around you at a certain height. So if you knew what height you were at, P of h will tell you the air pressure at that height. And h of t is your elevation as a function of time. So it's how fast you're climbing the mountain. This won't be a linear function. This will be something weird and complicated, but it'll tell you what your elevation is at every point in time. So with this setup, how would you represent the air pressure around you as a function of time? Well, the air pressure is this function p. But what do I want to put into this function? Well, I want to put in the height that I am at a given time. So I want to plug in h of t to this function. And if I plug my height at a given point of time into this p function, I will get the pressure that's around me at that point of time. Now, if I knew how fast the air pressure changes with respect to height, and how fast my height would change with respect to time, I can determine how fast the air pressure changes in respect to time by just multiplying these. But if I look at sort of the change in air pressure over the change in height, I multiply that by the change in height over the change in time. This gives me, ideally, the change in pressure over the change in time. This works for any sort of finite amount of time, right? If I want to say I know where I was at a certain time t1, a certain time t2, I could find the change in pressure there, the change in height, the change in time, and this relationship here would hold. So if I wanted to look at this using derivatives for these rates of change, what would I see? Well, I would see that this here should be the derivative of pressure with respect to height, and this here should be the derivative of height with respect to time. So what this here tells me that my derivative of pressure with respect to time should equal derivative of pressure with respect to height times derivative of height with respect to time. If I convert all those deltas to d's for derivatives, this is what I should see coming out of that formula. We have to be a little careful with this dp dh term because that's going to be a function of h. I have to plug in h values there. But this is the idea we're looking for. What does that give us? That leads us to the chain rule. The chain rule says if I want to differentiate a composition of functions, f of g of x, I get this by differentiating f of x, plugging in g of x. That's the fact that f only sees g values, like the pressure function only sees h values. So I can't plug in x into f. I have to plug a g value into f. So I plug in g of x here, and then I multiply by derivative of g, where I've plugged in x. This looks a little better in Newton's notation. F of g of x prime is equal to f prime plugging in g of x times g prime plugging in x. Or the way that hides a lot of these details is the notation I wrote before. df dx is df du times du dx for a function f of x, which is written as f of u of x. I most prefer this notation here because it makes sure you know what's going on and how to actually compute things. So what about those examples from before? Well, the from before we had sine of 2x. If I want to differentiate this, I can realize this has f of g of x is the function sine of 2x. So my f function, which is f of g, is sine of g, and I've plugged in g of x is 2x. If I put this in there, I get the function I started with. To differentiate this, I'm going to get the derivative of f, which is cosine, plug in g, which is 2x, have derivative of g, which is 2, which is my 2 cosine of 2x that we got in the first part. And the same works for e to the 3x as well. Another example, we want to find f prime for the function f of x, which is x squared plus 3x plus 2, all raised to the fifth. So the most common letter we'll use for the inside part here is a u, not g. So I'll reuse that notation here. So I'm going to write u of x to be sort of the part that's inside everything else. X squared plus 3x plus 2. Then my function f of x, I can rewrite as f of u of x, where u is that function, and the function f of u is u to the fifth. Because then if I put this in for u, I get the function I want back. Now I can use the chain rule to find this derivative. So f prime should be the derivative of my f of u function, which is 5u to the fourth, times the derivative of u, which I'll write as u prime for now. One more step gives me 5u to the fourth times u prime. U prime is the derivative of this u function, which is 2x plus 3. And now I want to plug u back into here to get everything back in terms of x. This should be 5 times x squared plus 3x plus 2, all to the fourth, times 2x plus 3. So there's the chain rule, the ideas behind it, and how you use it to find derivatives of compositions of functions.